Welcome everyone. In this lecture, I will show you that is how to prove Lagrange's theorem in straightforward method. And the content of this lecture has been taken from the book Group Theory in a Nutshell for Physicists by A.Z. So we consider a group capital G containing small n number of elements, and capital G group, it has a particular subgroup capital H, and capital H contains small m number of elements. Then small m is a factor of n. In other words, n by m is an integer. So this is the Lagrange's theorem, and we have to prove it. So the proof is as follows. At first we list the elements of capital H. So we are naming them in this way, that is H1, H2, H3, in this way up to Hm. It has total small m number of elements, and we have to note that since capital H forms a group, as H is a group, so this list must contain I, because we know that this is the requirement for forming a group. So one of the element described here is I, that is identity element, and we do not list any element more than once. Thus H is not equal to Hb, that is each of the elements are distinct, and Aj not equal to Hb for A not equal to B. We assume that small g1 is an element of capital G. This particular symbol means belongs to. So g1 belongs to capital G. G1 is an element for the group capital G, but this symbol is not belongs to. So g1 does not belong to capital H. So g1 is a element that is an element for the group G, but the g1 element is not contained in the group capital H. In other words, g1 is an element of capital G outside the capital H. Now we consider the list, that is we are multiplying g1 with the capital H group. So if you multiply each of the elements with small g1, so now we have the list, that is H1 g1, H2 g1, in this way, and we can take g1 outside the group H, and we can write the product in this way, that is H1 comma H2, in this way up to Hm, and we have written inside the bracket, and g1 is just multiplied outside of it. So this is a new set of elements, but this particular set of elements does not form a group, because you see that g1 is an element which is outside of the group capital H. If g1 was an element of the group capital H, then there will be redistribution or permutation, and that was the same group capital H. But as g1 is outside of the group capital H, so this particular list does not form a group. Now I claim that the elements on the list H1 g1 comma H2 g1, in this way up to Hm g1 are all different from one another. So this set of elements will be different from one another. So how to show that? We can prove it by contradiction method. For example, suppose for A not equal to B, so A and B are two different. So Aj g1 is equal to Hb into g1. So we are saying that two elements are equal. Aj into g1 is equal to Hb into g1. But if Aj into g1 is equal to Hb into g1, we can say that Ha is equal to Hb. Upon multiplication from the right by g1 inverse, this can be shown by multiplication from the right by g1 inverse. But Aj is equal to Hb, this suggests that two elements of the group H are equal. But this is in contradiction to our earlier statement, that is elements of H are distinct. So from the method of contradiction, we have shown that in this particular list the elements are different from one another. I also claim that none of the elements on this list are on the list H1, H2 up to Hm. That means this is a new list after multiplication by G1, and the first list is capital H, that is H was a subgroup. So capital H is the first list, that is H1, H2 in this way up to Hm. So now we are claiming that none of the elements for the new list and none of the elements on this list are on the list given previously, that is H1, H2 up to Hm. So how to show that? For some A and B, for some values of A and B, we assume that a particular element of the new list, that is H A into G1, that is equal to a particular element of the capital H list, that is H B. But this equality suggests that small g1 is equal to Aj inverse Hb. Now Aj and Hb, they are the elements for the group capital H. So Aj inverse is also contained in the group H, and the product of Aj inverse into Hb, that should be an element of capital H. So as G1 is equal to Aj inverse Hb, so this suggests that G1 must be in capital H, but it contradicts our assumption that G1 is not in H. So by the method of contradiction, it has been shown that no elements for the new list that are no elements are for the new list are contained in the capital H list. Now we pick another element small g2 of capital G and small g2 of capital G, not in the two previous lists. So g2 should not be contained in the two previous lists formed earlier. So we have selected g2 in this way. G2 is in G, but G2 should not be in the two previous list, and we again multiply G2 with the capital H group. Just we have multiplied G1 with capital H earlier. So this new set of elements will be formed H1 G2, H2 G2 in this way up to Hm G2, and we can write the product in this way. And I also claim that these m number of elements that have been generated are all distinct, and we can prove this just like previous way, that is by using the method of contradiction. So for A not equal to B, we are assuming Aj into G2 is equal to Hb into G2, thus Aj is equal to Hb, but this violates the assumption that the elements of H are distinct. So we have proved that elements, these new elements are distinct elements. I also claim that none of these elements are on the two previous lists. So the generated list is given here, and none of the elements should be contained in the two previous lists formed earlier. And again we can prove it easily, just we have shown in the earlier case. So for example, we are assuming that is Aj into G2. So we have selected one element from the just previous list is equal to Hb into G1. Hb into G1 is an element of this particular group. So if these two elements are equal, then we can show that G2 is equal to Aj inverse Hb into G1. We are writing as Hc into G1. Now Hc is an element for the group capital H. So Hc into G1, since capital H is a group, but this would mean that G2 is on the list H1 comma H2 up to Hm into G1, because you see the structure. Hc is an element for the group capital H, and this has been multiplied by G1. So G2 is equal to Hc into G1 means we have formed a group earlier by multiplying G1 with H. So G2 should be contained in that particular group. Why? You see the structure here, Hc into G1. Hc into G1 means G1 has been multiplied with an element of the group capital H. That means this list we have generated before. So G2 should be contained in this list, but which is in contradiction, to our assumption. So that means the list that we have generated last time, so those elements should not be common to the two previous lists. So we repeat this process, and after each step we ask whether there is an element of capital G left that is not on the lists already constructed, and if element is left, then we again repeat the process and construct yet another list containing small m number of distinct elements. So we go on repeating. Eventually there is no group element left, since G is a finite group, so eventually there should not be any group element left. And suppose we have constructed k number of lists including the original list, that is h1 comma h2 up to hm. This was the original list. So we can write it in general method, that is we have generated h1 comma h2 up to hm into gj, where j is equal to 0 1 2 in this way up to k minus 1. So the thing is that we have ultimately generated k number of lists, and in each list there are small m number of elements. So what is the total number of elements? M into k for k list, and each for and in each list m number of elements, and that should be equal to small n, that is small n is the number of elements in the original group capital G. So n is equal to m into k, that means n by m is equal to k. So ultimately we have proved the Lagrange's theorem, and I think I hope you have understood it, and for further understanding I refer to go through the textbook of AZ, and thank you for listening the lecture.